This conference will now be recorded.
Welcome, everybody. Today's this is the GEO AquaWatch special webinar. It is the first in a series of forecasting webinars that are leading up to our annual meeting on November 13th. My name's Dr. Mary Beth Neely. I'm the scientific coordinator for GEO AquaWatch. And it's my pleasure today to introduce our two speakers who are going to give us some information about the AlpLakes project, which involves a little bit of hindcasting and forecasting modeling of alpine lakes. Our speakers today will be Marina Amodori from IREA and CNR in Italy. And she will be joined by Albofazl Irani Rahaghi from EAWAG in Switzerland. And I believe Marina is going to kick us off.
Sure. Do you confirm everybody sees the screen in the right way, right? Okay, so thanks Mary Beth for the nice introduction and for those attending this webinar. So Fazal and I, together with our colleagues in the AlpLakes project, agreed on this title for this webinar, which is Towards the Symbiosis of Hydrodynamic Models and Satellites, because we believe that this is really the title that is somehow summarizing the philosophy and the aims of this project, which is a funded project within the Alpine initiative. So before going to the details of our work, let us introduce the full team. So you can see that we grouped together many funny pictures of our colleagues. So we have a lot of people from remote sensing from both this EAWAG institution and IREA CNR in Italy, Dani and Mortimer from EAWAG and Claudia Mariano from CNR, who contributed for the remote sensing part of the project. While for the modeling, we have our PI, Damien Bouffard, who is from EAWAG, and he's this guy here on the top right of the picture, and Marco Toffolon from University of Trento, who were the modeling experts of the project. We benefited from the support, the strong support of a software developer, who's James Runnels here in the bottom right slide. And then I put in the middle the pictures of Fazal and me, because we eventually became a weird kind of hybrid between remote sensing and modeling, which was very useful and fruitful. So Fazal was mostly dedicated to the satellite part, and he will explain more in detail what was his work together with the remote sensing people, while I took over the part of modeling. So what do we need integrating modeling, satellite products, and in situ data? I think that besides, apart from the fact that this is a nice figure to show, we all know which are the strengths and the weaknesses of modeling and remote sensing and collecting in situ data. So for modeling, we can choose what kind of spatial and temporal scales we want. We have the full control of all processes in a three-dimensional way if we are using a 3D model, of course. And the most important weakness is, of course, that we need data for validation. Satellite products are extremely useful in this sense. They are cheap many times. They're free, provided from national agencies. There is a mic. It's possible to. I can hear myself. No, that's not anymore. Thanks. So, satellite products are available for many different quantities, and they provide a very nice 2D coverage of many physical and biological quantities. They provide regular sampling, so they are extremely used in many applications. But for the optical products, we know that we have issues related to cloud, and actually they provide a picture of what happens at the surface, and they maybe go below a few meters depending on the euphotic zone. So this is a weakness, we can say, of satellite products. Finally, in situ data provide a fine temporal resolution if we put continuous monitoring. We can choose where we want to measure our data. They can be expensive, actually, but they also lack a little bit of representativity because the picture they give really depends on where we put our instrument. So it is clear that if we combine the three boxes, then the three cubes, then we have the full description of what we want. So how is this combination usually done? So in modeling freshwater resources and lakes in particular, lake surface water temperature is the quantity I would say mostly used in most works and projects. So I put here one example of how validation is usually done with lake surface water temperature. You have a 3D model, like they're 3D in this case from Lake Garda, and you compare the simulated water temperature with your satellite products dataset, which is in this case the CCI dataset for lakes. So this is a very nice way to validate your model. It's a very nice picture. It's somehow describing a success in terms of modeling. And similarly, many applications are extensively using lake surface water temperature for assimilation, which means that we have a model that is running, and once a new satellite image is available, which in this case is from AVHRR, we compare what we get from the model and from the data from satellite, and we eventually correct the model such that if it was going in the wrong direction, it's somehow forced to keep the right path. So this is a very nice way to use data, and it's very similar to what is also done with in situ stations in weather forecasting models, for example. But what I think is interesting from both validation and assimilation is that they correct the model, or they allow us to assess the model's performance, but they don't help us to improve the model in a really coupled and integrated way, because water temperature is a result of the model. So once we have water temperature, the model has already run. So we cannot say this is a real integration from my point of view. It's just a wise and brilliant way to use this data. So what we asked ourselves in AlpLakes is, what can we actually use that comes from remote sensing and that is actually able to transform the results of our model? So no, we are not improving something that is done, but we want to use remote sensing derived quantities to improve the model. And so we thought about water transparency. Water transparency is a quantity that is actually possible to be retrieved from water leaving reflectance, and it is a quantity that is actively used in models. So I'm showing here an example of what it is done in the depth 3D model with water transparency. So we provide the model water transparency as a Secchi depth information. This is used to calculate the extinction coefficient. And then this gamma here is used to parameterize the income of heat from the surface to the interior layers. So these plots here are showing the evolution of this heat from the surface to deeper layers in different hours of a day, in a summer day. No, this is March. So in a spring day, from the surface to the interior layers. And so what we see is that if we increase the value of Secchi depth, that is transparency for us, from 0, which is of course an asymptotic value where we're not putting 0, otherwise we would have infinity in gamma. But anyway, the smaller the Secchi depth, the higher the energy given at the surface, and the lower energy is transferred to the deeper layers. So if we look at the numbers, we see that if we increase the Secchi depth from 0 to 10, we actually are reducing the heat at the surface in the warmest hours from 600 watts per square meter to 25. Of course, the integral will be the same because we're just saying it's not totally absorbed at the surface, but it goes below. But the result in terms of model performance of this simple number that goes from 0 to 2 to 5 to 10 is actually impressive in terms of heat. And if you're wondering what is the effect in terms of temperature, I'm showing it here. It's another day, it's in summer. Of course, the difference is much more evident during the summer days. And what you see is that for very small Secchi depth, you have a very high temperature at the surface and almost no change in the interior layers. So it's warmer at the surface, cooler at the interior, and the water column is very stable because there is a strong stratification. If I change this number from 0 to 2 to 5 or to 10, the shape of the thermal profile completely changes, and also the values of temperature are drastically reduced from 32 degrees at the surface to 23. So it's almost 10 degrees of difference by changing from 0 to 10 meters of transparency. So it is clear that this information is really important. What we usually do is to collect with this kind of data with Secchi depth measurements in situ, but sometimes we just take one value in one point, while the great strength of remote sensing products is that we can actually see the spatial variability. So this is an example from Lake Geneva on 22nd of August in 2023. And we see that there was a strong variability. We have almost 2 meters of Secchi depth here and almost 6 meters of Secchi depth here. So water is much more clear in these areas than in the yellow areas. So we have spatial variability of transparency and also temporal variability of transparency, because this number will change if we are during a bloom or if we are in totally clear water conditions. And this also relates with turbidity, of course, which is a quantity that is typically obtained from remote sensing. And in this case, it's total suspended solids. So we are talking about concentration. And we see that water clarity, of course, reflects TSM. And we also see that the way solids are moved, or either blooms and algae are moved inside the lake, also depends on the flow field. So we have transparency that is affecting the way heat is transferred and temperature is stimulated. But we also know that what we see in terms of suspended solids and chlorophyll is the effect of circulation. So the big challenge is, how can we use this information to really have a model that is working for both simulating water temperature and flow field. So the challenges of our project were clearly on different aspects for the remote sensing, modeling, and of both aspects. So for remote sensing, the great challenge was to produce water quality products based on apparent optical properties of water, and for different lakes with potentially different optical water types. And we also had to deal with the lack of this kind of data even in our lakes that are, we can say, quite well monitored, at least for some of them. For the modeling part, we wanted to have an operational forecasting model for all our lakes that are very different one another. And we also wanted to couple those models with a particle tracking module, such that we could implement the information of suspended solids and chlorophyll into our pipeline. So in terms of the combined challenge, we wanted to integrate the information of satellite-derived transparency products in lake models, and in particular in our Del3D. I won't go too much in details on the modeling aspects, because I know that the community of GEO AquaWatch is more sensitive and thrilled by remote sensing topics, but this also actually required us to tightly modify the Del3D heat fluxes parameterization, and then finally to couple TSM products to particle tracking. The overall aim of the project was to do everything in a consistent and automated way, such that the structure that we developed is now ready even for further upscaling. And of course, we wanted to maintain the rigor of a scientific work, which could be fundamental for new investigations, but also we wanted to have a tool that was open and accessible for all kinds of users. So I will quickly steal 1 or 2 more minutes to Fazal to describe them very quickly, the modeling aspects, what I think is more interesting, and then I will give the floor to him. So modeling. The greatest challenge of modeling was that we had different lakes, all located in different altitudes, different shapes, depths, sizes. So you can see on the right-hand side here the grids, the numerical grids of all these models. You can see that they are ranging from some square kilometers to hundreds of square kilometers of area, and depths going from 350 to 330. So of course, for all these lakes, not all processes play the same role. So it was important to have a method that was able to provide a good model for all of these lakes. And at the same time, as I said at the beginning, these are quite well monitored lakes, but still for some of them, there was not the total availability of data. So these are lakes that have maybe in some cases hourly data in terms of temperature. These are temperature profiles from surface to bottom of all the lakes. In some cases, we only have monthly profiles. Some cases, we have 2 or 3 profiles per year. So we needed to design a calibration procedure that was able to handle all these differences. So this required defining meaningful performance metrics and the key parameters for calibration. We developed our own strategy, but we built it on scripts and algorithms available in literature. In particular, we used an automated algorithm for calibration of 3D models that is called Dynopods. So in the end, we calibrated the 12 lakes in the same way, each one having his own parameter. And for doing this, we ran at least 200 runs per lake. I conclude with some examples. So we have, for example, the results in Lake Shu, data and model, Lake Garda and Lake Agri. They are very different lakes with different data availability. And what we can see is that we could actually reach 1 degree, at least maximum 1 degree of root mean square deviation all along the year and all over the water column, which is, I don't know how many of the attendees are familiar with performance metrics of the 3D models. This is actually a very good result, also considering that it was performed in an automated way. So I think that I will give the floor to Fazl now. So Mary Beth, if you want to switch to present mode.
Thanks a lot, Marina. Can you hear me well?
Yes.
Yeah, okay, wonderful. Okay, so hi everyone. I'm trying to share my screen. My name is Albofazl Irani and I'm a postdoc working at EAWAG and University of Zurich. Okay, do you see my screen now?
Yes.
Okay. So thanks again, Marina. So now I will give you some overview of our remote sensing activities, as well as the particle tracking. You know, what kind of features do we have there? And I will finish by showing a scientific test case from Lake Geneva. So as Marina mentioned, our 2 main satellite, target products are SekiDeps and TSM. And we mainly targeted, to get the products from Sentinel to MSI sensor. However, if you go to our website, you would see that we also have color fill, products, and also like TSM and SekiDeps from Sentinel-3 Olchi, which is linked to some of our past, CalVal activities over Swiss lakes. If I want to summarize our CalVal activities, I can split them into 2 main subtasks. The first one is validating the atmospheric correction algorithms, for which we selected 3 atmospheric correction techniques: polymer, C2RCC, and acolyte, based on what we saw in the literature, and also from our past experience with some of those test sites. And then we also got the in situ measurements from 2 main sources: the in situ AOP data, and mainly by AOP here I mean remote sensing reflectance mainly. That's our main target product for this part. We got it from field campaign, as well as a few automated stations over 3 of those sites. Then we did the matchup analysis and find the best performing atmospheric correction, and then we went to the next step, which is calibration and validation of biooptical algorithms to get the downstream water quality parameters. For that, we also conducted some field campaigns. We also got the measurements from historical measurement by environmental agencies for some of those lakes. Okay, so if I wanna give you an overview of our AOP measurements. So as I mentioned, we had automated stations in 3 of those sites: Lake Geneva, deep pre-alpine large lake, Lake Garda, again a very deep and large lake, and Greifensee, which is a eutrophic lake in Switzerland, smaller than the other 2. And the data that we took for our AOP validation was water insight display station from Lake Geneva and Greifensee, and also we got the IPSTAR data from Lake Garda. Here you can also see the summary of our field work that we mainly used handheld VISP-3 to take the AOP. So our research objectives were first of all, to investigate the spatial resolution effect on the atmospheric correction performance for our sites. Then we also wanted to assess, the pixel aggregation effect on those performance. Like in this regard, comparing a single center pixel with a 3x3 aggregated one, using the median of those 3x3. And then also seeing if we can have a generalized AC which is feasible for all the test sites or not. To go from level 1 to level 2 in situ data, we did some basic quality checks. Then we estimated reflectance using 3-component algorithms by Philip Grotresch et al. And then we also implemented clustering and scoring by Wei et al., which basically has 23 predefined clusters, and then score and clusters your measurements. And then we removed some of the spectra that were they had lower scores, or if they were in the weird clusters. As for the algorithm selection logic, so we compared 12 combinations, as I mentioned, 3 different ACs, 2 matchup box, 1 by 1 or median of 3 by 3, and also 2 spatial resolution, 20 meter and 60 meter. And our primary performance metric was median symmetric accuracy. Well, we also calculated other performance metrics, but for selection, we focused on this metric. Here is a summary of our AOP validation over those sites for all the sites that we had matchups. So these are color coded. So the blue greenish are they had better performance, whereas the pink and red one has higher errors. As you can see, for most of blue to green, region, so we had not satisfactory performance. Whereas for the near infrared, only Lake Geneva and Lake Zurich performed good. So we speculate this is due to an extra glint correction that was done on Lake Garda data as compared for the others. So this is currently in progress by Mortimer Werther in our team, and he's going to make them hopefully better and get the better performance metrics. And here in this right panel, you see, the best performing ACs. What is obvious is polymer is dominant for most of the lakes, except for Lake Garda and Lake Saint-Moritz, which I would say C2RCC performed better, and also for Greifensee, which Acolyte was, the dominant one. For Greifensee, we could expect this because, as I said, so this is a eutrophic lake, and we know that Acolyte performs better there. As the downstream product, so here you can see our preliminary, matchup analysis on the SECI products. So these are, so for the moment, we only focused on the lakes that we have AOP measurements, and Lake Garda was the only one that we had robust matchup data set. So you see the median symmetric accuracy is around 30%. And here you see the time series of the retrievals over the course of a few years. So our next steps is to add other monitoring sites without AOP measurements, and also a big challenge for us is how to implement this SECI calorimetry on our operational platform. So this is also something that we are dealing with for the moment. And for TSM, as you can see, so we use the WOPTIS technique, which is a single band method, and for that, we optimize this 80 calibration parameter as 665 nanometer for all the lakes that we had data for. And as you can see, the error is around 40% the median symmetric accuracy. So satisfactory, but it could be improved. So with this, I would like to switch to particle tracking section. So particle tracking, here you see, so we implemented and tested particle tracking for all the test sites. And if I wanna, express what was our main objectives. So basically, we aim to track the fate and origin of observed satellite patterns. So not for the sake of just observing and tracking them, but to improve our understanding of the lakes. And also, for some other applications, we want to investigate the dominant water pathways. So it could be like if you are interested in surface processes or in deep processes. So depending on your interest or use case, you can implement those particle tracking and get the final results and see what's going on. Also, this particle tracking can be improved your sampling strategy, both in time and location, and also if you are interested in short term or long term, so you can run the particle tracking in short term or long term as you wish. If I want to give you the conceptual design, so imagine that you have a satellite overpassing day 0. So then we convert those dominant patterns that you see here to particles, and then we get the results from 3D hydrodynamic model that Marina already mentioned, together with the having the circuit products to improve the model, and then track those particles over the time. And then we got the the particle locations in our desired time, day 1, day 2, or whatever, and then we can compare what we observe with the upcoming satellites. So this is the very basic concept of the particle tracking, but it's not the only application. So for example, as I mentioned, so you can release some particles at your location of interest and track them over time, or even track them backward to see where do they come from, so they find the origin of those particles. For the approaches that we already implemented in AlpLakes, so we have 2 different versions of particle tracking. One is online, a simple advective model, in which you can interactively see the particle, visualize them, and get a first grasp of what's going on in the day of your interest. So this is only available in forward mode and also not much flexible in post-processing. Whereas we also have an offline version, which is based on this TrackMass model, which is a well-known model in this particle tracking community. Is flexible for particle seeding, available both in forward and backward, and you will have much more freedom to process the data. You will get the results. You can do your own post-processing. And it's also we suggest that to use this one for your scientific adventure. So it's much more reliable in our view. And all the codes and conversion can be found in the public repos, as we also show at the end of the presentation. Just to show these 2 approaches, so this is a TSM map from Lake Geneva on mid-August this year. So here you can see we saw this hotspot here. So we release some particles and then track them in forward mode. This is a simple advective version. If you go to our website, you would see that this hotspot would go follow the northern shore, and then at some point it will come back to the southern shore from the middle of the lake. Whereas in this simple advective, you won't see such a pattern, but you see that it will follow the northern shore. But this is the same tracking, but using the offline, more sophisticated version. And as you can see, this is more in line with what you can see from the satellite. So this is a very simple example of these 2 approaches that we have. So with this, I'd like to go more into more exciting and scientific applications of the tools that we develop. So this is a picture of the algae bloom in Lake Geneva from early September 2021. And as you can see, there are like so much interesting Bangkok like pattern over the lake. So if I want to give you some background, so Lake Geneva is more or less a clear eutrophic lake. So typical lake is like this, so it's not so dirty, if I want to put it in a simple word. But this is the picture from the same day from the southern shore of the lake. And as you can see, there is this brownish particles more or less all over these areas. And also people reported this fishy odor, which is linked to this Uroglena microalgae. So the question was like, what's going on here? So first of all, we got some remote sensing signals. So we looked at this Sentinel-2 MSI and converted, the level 1 to chlorophyll concentration and Secchi depths. As you can see, the chlorophyll concentration can reach up to like more than 80 milligram per cubic meter, which is quite high for this lake. And Secchi depths are in some regions are less than 2-3 meters. And if you look at the long-term monitoring data over the lake, we would see that this event is very, very unique. And also, we also looked at Sentinel-3, and we could confirm that the bloom started from the southern shore. As for biological footprints, so our colleagues at INRA in France, they took water samples and confirmed that this is linked to this Uroglena microalgae, as I said. So this is not luckily toxic, is a non-toxic algae. However, they like to live in colony, and they very much like the calm condition to float close to the surface and grow. And for the history of Uroglena, so in Lake Geneva, it was only reported end of July, beginning of August 1999 from the local authority monitoring monitoring of the lake. So then we ran the 3D hydrodynamic model, which was our first tool. And when we processed the data, we could, confirm that there is some coastal upwelling happening in the southern shore, as you can see here in this, reddish hotspot here. And also, like if, for example, look at this transect P0, P1, which on the right panel you would see the temperature. This black line shows the thermocline, and the thermocline is tilted in this southern shore. So all of them are like a signature of like having the coastal upwelling a few days before the bloom. And we also looked at the surface current, and we did some principal component analysis for over the course of like a few days before the peak of the bloom. And we could indicate a three-gyre structure, which if you compare with the satellite observation, we can see that they are more or less linked to these main patterns that you see here. So that was the second clue for us. And then we started to run the particle tracking. So we released the particle in the point that we expected, coastal upwelling, and track the particle forward in time. We see the particle the day that we expected is the onset of the bloom, and we continued until the peak of the bloom. And as you can see, so for example, this mushroom-like structure that you see in the western part of this event was quite nicely regenerated. We also ran some backward tracking, which for the sake of time I cannot show here. So we could also confirm the other gyres. And the main message from all this analysis was that the bloom has some origin from the shore. And some of our colleagues, they also did some carbon 14 analysis, C14 analysis, and they could also see some terrestrial origin from the waters close during the peak of the bloom. And then we came up with this, hypothesis on the bloom formation and dispersion. So we looked at the meteorological data, both in long-term and short-term. So here you see the short-term meteorological data, wind speed, wind loss diagram, and this is the solar radiation and air temperature. So we observed that there is a relatively calm, warm condition after the bloom onset. So from 3rd of September, if I want to put it here, which is favorable for bloom formation and growth, especially for Ruclena. And then we saw that right before this calm condition, we have this, high wind, strong wind condition, unidirectional, which can, support the observation of this coastal upwelling. And we believe that, it has brought some of the particles from the deep water to the surface, so fabricate a reactor for the bloom formation. And then we went back and looked at other climatological parameters, and 2021 wasn't a special lake around, in the vicinity of Lake Geneva, except for heavy rainfall and a bit of flooding during, July that year, as you can see here indicated by this red spot of water level anomaly. So this was, however, like 6-8 weeks before the bloom. So our hypothesis was that because of this flooding or heavy rainfall, so we had these terrestrial, particles going into the lake. They stayed there, and then because of this coastal upwelling, they came to the surface. And since this coastal upwelling was followed immediately by this calm, warm condition, then they could help the growth of Ruclena, and with the help of hydrodynamics, we had the dispersion. So to test our hypothesis, we looked at the longer term measurements from 1998 to 2022. And these are all the favorable conditions. So for example, here the blue shows all the days that we had precipitation a few days to a few weeks before, up to 8 weeks. And this strong wind is the orange one shows the days that we have strong winds a few days before. And this calm, warm condition are all the days that we had those conditions a few days after those days. So, and then we come up to test it. So we convolve all these favorable conditions together to see how often we see the sequence of all these three requirements for the bloom formation. So basically multiplying this probability together for all the 24, 25 years that we analyzed. And we surprisingly, we saw that only, July 1999 and, September and July 2021 was, they had high bloom occurrence probability, which coincides with the years of observing Ruclena bloom. So with this, I would like to hand over again to Marina, and I guess she's going to finish up by some summary and conclusion, and also giving a demo of our AlpLakes platform. Yeah, thank you very much.
Yeah.
Marina, are you there?
Yeah, I'm here. Thank you, Fazal. So just to summarize a little bit. Oh, okay. So I'm becoming.
Oh, okay, I can do this. Yeah, I can continue. Yeah.
That's fine. I am representer now.
Okay.
Okay, so let's go back here. Here. So everything works?
Yeah.
Yeah. So just to summarize a little bit and conclude what we have seen from also the nice slides from Fazal, we see that combining all these tools helped us to explain a short-lived algal bloom, but also we were able to reproduce the patterns that we saw from chlorophyll products and transparency and TSM. But also, as Fazal clearly showed, this we can say episode also helped us to go on longer time scales and to deliver some conclusions on 20 years of observation. So since this kind of mixed studies is not so common, we were trying to replicate with another case study, and we are currently working on resuspension events in southern Lake Garda, which are very common. So I will not go into the details of this case study because it is still under investigation, but I just reported here a time series of resuspensions that are clear from TSM maps in Lake Garda. This one occurred in October, from October to December 2017. And we could see from the southern part of this lake clear structures, vorticos and gyre-like structures of suspended solids. And so, since differently from Lake Geneva, circulation in Lake Garda, especially in the southern part, is not still so fully described, we will benefit from this kind of information to describe gyres and areas of calm, velocities in the lake. So as the GIF is showing on the right hand side, it is quite clear already that we have a combination of vortices moving in opposite direction that create favoring conditions for resuspension and then the transport of this material. So stay tuned on this new subject for the months to come. So what is this AlpLakes providing? And as you will see then, similar web platforms. So we have shown the tools, but we haven't talked a lot about the web platform. So actually all the tools that Fazal and I have been describing are available on a web platform. I will show a very quick tutorial after this slide. So this kind of experience helped us combining information and tools, but also it was very exciting for us to collaborate and exchange knowledge with experts from different fields. This is the only way to have original and interesting research questions, in my opinion. And of course, there is still a lot of improvement. So in this regard, for those attending, if there's anybody interested in investigating the lakes that are within our network, of course, they are totally free to download all the data that they need from the platform. I will show you how to visualize and download data. For those who are working on Alpine lakes, which might be interested to be uploaded on the platform, this is also possible if they want to reach out to us. But it is also nice to say from my side that we have completely open repositories of all the tools, start from the calibration to the remote sensing production to the API and all the software infrastructure. So for those who are interested in set a similar pipeline for their region, for their lakes, it's absolutely possible to replicate our study. Of course, they might need some guidance, but all the necessary tools are there in GitHub Open Repository. And of course, if anybody is interested in having new ideas and joint research together, that would be great to discuss and to find new science case studies. So as Marybeth advertised in the chat, we would also like to invite you to fill in our questionnaire as soon as it will be ready. For those who are subscribed to the newsletter of GEO AquaWatch, they will receive the email. If they are not, they can also get the survey reaching out to us or with other ways that Marybeth maybe will explain. So very last slide. I don't know if the video will start. If not, I will make it start from my computer. Yeah, that's the case. So be patient. There it is. Sorry, it's not here. It was supposed to be very quick and instead it's not. Sorry for this. So shall I stop a little bit my sharing because I will have to search for it.
Take your time. Go ahead and search for it. We will. I'll take just a minute to let everybody know that if you would like to receive the survey and you are not registered for the GEO AquaWatch newsletter, you can send your email to one of the presenters today. They will put their emails in the chat, or it might even have been on their slides. And if you are registered for our newsletters, you would have received a reminder about today's talk and that way you'll know you don't have to sign up for that. Are you ready to try your video now? Okay.
Yeah. Okay. So the video was prepared by our software developer, James Runnels, together with our PI, Damien Buffard. There is a voice that is from James, but just to be quicker, I will talk over it. So sorry, James, for this. So basically, this is the website. You can all go on this link, and then what you will see is the homepage with all the list of lakes. They are they have a very quick description of the lake, and then you can also choose to sort them by different parameters like morphological features, depth, etc. If you click on any of them, you will have a preview on the 5 days forecast since the day uploading. So you will, if you go now, you will see the 11th of October with 5 days forecast. You can run the simulation for this forecast and play and pause and go next. You can select the time you want to visualize. So for most lakes, data are already available since I think April 2023, but there will be also further uploads for the past. You can choose and customize the visualization as you prefer with scoop or screen and changing the background and many other options. Then, since these are results from the 3D model, you can also choose to have different layers and to plot the results at the different depth of the lake, because these are from the results from the 3D model. So at the moment, we are looking at 30 meters depth. Now James will click at the surface back. And so we are actually seeing the simulated water temperature and the flow field at the surface. So this is an example of how to choose another period of time, which can be of any length. Of course, the longer the period, the heavier the data to download, but I mean, it will be up to you. So you can also personalize a little bit the visualization of the layer if you want to remove arrows and choose streamlines, which actually I prefer because they're very beautiful to see and also clearly show the transport occurring in the lake and change all the visual aspects. And then, yes, now he's showing some options that are possible here. And also all the palettes are customized, can be customized. This is because you can download the data as they are, but you can also download a picture and an image. So you can actually choose what you want. So I will go a little bit faster. I think now you can add layers. So you see here all the layers you can add. For example, if you want to make it compute thermocline based on the scripts that we have on the PyLake. This is also available on GitHub if you want to calculate it by yourself on the results of the model. And then there's other layers that can be added, as for example, here it is possible to look at transects. As I said, it's a 3D model, so it might be interesting for you to search, to look at the velocity field or a temperature field in a three-dimensional way, also looking at what happens in the transect. So I will move a little bit faster. Many plots can be merged together in a subplot way. So here we are visualizing temperature, transect, and also the variability in time in one point. And similarly, you can release particles. So we'll go quickly here. So particles can be added. So this is what Fazil was showing before. So you can choose where you want to put your particles and see if they move and how and where. Again, this is following the field that is given in the visualization here. So you see that you can follow the gyre. And I think that now we will move to Sentinel products. So as I said, this is an integrated platform. So we have model results, which have been looking at together so far, but then you also have satellite products. And so they are automatically uploaded on the platform. And you can also see when data is available and with what percentage of surface cover. So as for example, for chlorophyll or for turbidity or transparency, secu depth. And for many lakes, you also have the possibility to choose between Sentinel-3 and Sentinel-2, which of course will have a difference in terms of spatial resolution. And I think that we can, yeah, you can also customize the background if you would prefer this kind of visualization and change the opacity. So these are all other details that I really recommend you to test and check yourself. So yes, so maybe there's not a final part, which is interesting, but if you click on the API button here, then all what we have been looking at together can be actually downloaded. And so any kind of post processing that is useful to you can be actually done on the raw data. And that was it. So thanks a lot. Thanks a lot for listening. And yeah, I speak also for Fazal, saying that I'm looking forward to receive questions, if any. And thanks for your
you.
time.
Yes.
Great. Yes. What an impressive system you have there. And wonder, do we have anybody in the audience who would like to unmute and ask their question directly, or you can also type it in the chat if you do not feel comfortable speaking out loud. Bob Bishop.
You are muted, Bob, sorry. You are muted.
Let me see if I can unmute you.
All
Yes.
right. Well, thank you so much.
Oh, there you go.
It was excellent. I'm here on the coastline of Lake Geneva, so that was the most interesting information for me. I have a question: whether the data, the satellite data, I notice it's Copernicus Sentinel-2, is it hyperspectral or multispectral?
No, that's multispectral. So
20
I think,
channels.
sorry?
20 channels, right?
No, less, I think. I don't remember, but it's less channels. So in total, we also only work with the optical channels. So in the optical channels, we only have, I don't recall, maybe 6, 7 in total, 6 channels. I don't remember exactly. But no, this is multispectral. But for the hyperspectral, we are looking forward to have PACE soon. And also, like Prisma Vision is one of the ones that is currently available. Like you can ask for the data. Yeah.
Okay. Well, that'll be extremely interesting when hyperspectral becomes available with
yeah, exactly. Yeah.
200 channels. Good. That was my only question. Thank you so much.
Yeah. Thank you.
Alex, I think you're next.
Yes, thank you, Mary Beth, and thank you, Fazal and Marina, for the very interesting presentation. I think you covers a lot of subjects, so I have a very narrow question, I think. But so first I wanted to leave this appreciation for your presentation. The question is for Marina, I think, which is related to the validation process, because I'm not used to satellite surface temperature products in terms of their uncertainty, but I know from the biogeochemical products the uncertainty can be quite high. So you're validating the models against the satellite data. So the question I have is, what is the uncertainty inherent to the satellite retrievals when you do this cross-validation of your models against the satellite retrievals instead of in situ data? And then connected to this question is there a plan or an interest to support also to have included in situ data? So for example, the aspect is you can validate maybe the surface temperature patterns with the remote sensing, but other aspects that also affect the biology and ecology process, for example, depth of the mixed layer, they depend on some vertical resolution. And in that case, how you validate the vertical aspect of your model if you don't have in situ data. And so if you can comment on those two aspects, it would be very interesting to know more. Thank you.
Sure. Thanks for the question. So actually, the models were calibrated and then validated against in situ data, so not with lake surface water temperature from satellites, at least in this version of the project, where we wanted to have a three-dimensional model that were actually representing the vertical structure of water temperature first. So the inclusion of lake surface water temperature as something that can be assimilated or used for validation is something that was actually present in the former version of this platform that will be included again in the future, also thanks to higher resolution products like from Landsat, as for example, because some lakes are small, so you cannot really use AVHRR for small lakes. But actually, the models were calibrated and validated with in situ data, actually. So we had, as I showed, there was a plot with modeled and observed water temperature along the water column. And we evaluated both the performances in general in terms of root mean square deviation, but also we compared the Schmidt stability of the water column of the entire lake, actually, from model and from data. So I agree with you that validating only with lake surface water temperature cannot be a good idea in general. And that's why I started saying that lake surface water temperature is great for detecting spatial patterns, for having a fast validation of what happens in the surface. But then you really need also in situ data and vertical profiles for trusting your model. So I totally agree with you. And for the accounting uncertainty, I'm not really the right person to reply in terms of lake surface water temperature. What I can say based on my past experience is that since there is a large uncertainty on the absolute value of water temperature from satellites, because they refer to the skin layer, which is not exactly the temperature that you collect in situ. In that case, what I'm used to do is to look at the spatial pattern rather than trying to match the exact value of water temperature. So this was an exercise we did in Lake Garda, and that was really satisfactory to us, because even when there was a small bias between the model and lake surface water temperature, which could be accounted for, which was accounting for the difference in the source of the quantity, still we could verify that the spatial distribution was in good agreement. That means also that we are properly simulating the flow field. So there are also interesting connections between velocity and temperature, which is basically a tracer also in lake. I'm not sure I fulfilled all the...
Yes, indeed. Fantastic. Thanks for clarifying my questions. I misunderstood a bit then the validation aspect, but thank you for the full response.
So
if there's time, just a short comment on Alex's question. Yeah. Thanks a lot, Alex. But just to announce, maybe now, since a few months ago, we have started a new project on lake surface water temperature retrieval, for which we have 2-3 automated stations. On those sites, we have skin temperature measurements and bulk temperature measurements. And I totally agree that those products could be with high uncertainty, but we will try to see if we can come up with good products. And for the model, you are absolutely right. So the model sees the bulk temperature, whereas the satellite sees the skin temperature. So we have some ideas to do this conversion, to account for this skin effect, skin to bulk. And so this is something that perhaps AlpLakes 1.2 would be would come with this lake surface water temperature. Just a short announcement.
Okay, we do have 2 final questions. Hopefully, folks can stay a little long. One comes from Annabella Farrell. She says, "Congratulations on an amazing project. Does the same Secchi depth cause different thermal patterns if you consider different water components in your model?" Just a quick answer, maybe.
I'm not sure. Yeah, but it's the other water components. So just to clarify, our numerical model are pure physical models. So we don't have any biogeochemical model. So we don't have any water components included in the model. Even our particle tracking, I should emphasize that we have inert particles. The particle, they don't have any weight. There's no Clausen rate, so they are inert particles. But still, so this is the first step. So Marina, if you want to add something, please.
Yeah, I think it can be actually a very interesting question if if the idea is that if Annabella is referring to the special patterns of transparency, because what we've been doing so far is including water transparency in our physical models. So again, there's just one type of water in our models, unless the difference is related to density. But we are using just one value per lake, and this value changes in time according to the satellite's retrieval. But it is actually possible that giving a spatial pattern of transparency will eventually improve the model even more. This is something we observed with Fazal as well, because where we have shallower Secchi depth, you will also have higher temperature in the surface, while where you have deeper Secchi depth, you will have cooler. This is not, of course, a linear relation, but you expect this, and you observe this also from lake surface water temperature and transparency products. So including Secchi depth in a spatially varying way, and not only in a time varying way, would actually affect the thermal pattern for sure. Of course, we are talking about effects on the single event or on the single episodes. I would not expect a long-term effect of such special variation into the overall performances of the lake model. But if you look at water temperature on that moment, if you include this information from the transparency variability in space, I think that would also affect model performance.
Okay, thank you very much, Marina and Albofazl. I was disconnected a little, but yes, I see patterns, and I believe that some patterns are different for different kind of algae, because of the thermal efficiency of each components in that kind of species. So that's why I think it would be very interesting to study the temperature patterns with the blooms and different components of water for the same Secchi depth. So thank you very much.
And everybody join us on October 25th, when Annabella will be our first Early Career Society Water Talk. I put information about that in the chat. And our final question comes from Natalia Licenza for Fazal. She asks, can you go, and I will just request that it be maybe under 2 to 3 minute explanation. Could you please elaborate on the bloom occurrence probability?
Yes. So as I mentioned, so this Uruguayana is very specific, type of microalgae. And this probability, as I mentioned, based on the lessons that we learned from 3D model and hydrodynamic model and remote sensing, we could come up with a scenario for the, some sort of sequential events that are like necessary for the bloom to occur. And then we somehow mathematically formulated those, occurrence, into the probability. So if I want to give you an example, for example, for heavy rainfall, we looked at the long-term, data and just took the 99 percentile as the threshold and put a value there, and then converted with the sigmoid function all the measurements to the probability, and then scale them between 0 to 1 to have, the normalized probability. So there are some mathematical formulation behind those, and those are based on measurements and observation for all the 3 requirements that we listed for this specific balloon. So I hope this is the answer to your question, but please reach out if you need more information.
Yes, thank you very much. One last round of applause, virtual or otherwise, for our speakers, Marina and Basil. Thank you all for remaining a little late today, and it was much needed information. And what a wonderful kickoff to our water quality state of the science in forecasting series. We hope you'll join us again on October 26th for a 2-parter, and again November 7th. And then the culmination will be our discussion in person at the biennial meeting on November 3rd. Thanks again. The posting of this recording will happen later this afternoon or early tomorrow morning. Thanks, everybody. Have a great day.
Thank you very much. Thanks for having us.
Thank you.
Yeah. Have a great day, night, morning. Yeah. Ciao.